Hello everyone. Welcome to this video, the last one in our series on transactions and concurrency control. So we are going to look at serializability today. So we have already discussed in our previous video about classification of schedules based on recoverability, and we had seen recoverable schedule, non-recoverable schedule, cascadeless schedule and cascading schedules, and also strict schedule. So there is another classification of schedules which is based on the principle of serializability. But to understand serializability, we have to understand what is a serial schedule. So a serial schedule is a schedule in which every transaction that participates in the schedule, all the operations of that schedule of the transaction are executed consecutively in the schedule. That means there is no interleaving of operations among transactions in a particular schedule. So that is called your serial schedule. And if it is not like that, if there is an interleaving of operations among the transactions, then this is a non-serial schedule. So as you can see here, the first one, schedule A, is a serial schedule because all the instructions of transaction T1 are together followed by all the transactions of all the operations of transaction T2. However, C and D are non-serial schedules because you can see that there is the interleaving of operations between the transactions. So first T1, two instructions of T1, then two instructions of T2, then T1 again, then T2, then again T1. Similarly, in D also, that the operations between T1 and T2 are interleaved. So this is a serial schedule and a non-serial schedule. Now, a serial schedule, usually we assume that it is always going to give us the correct output because there is no interleaving of operations. So we assume that the serial schedule will always give you the right answer. But the problem, as we have seen, happens when instructions are interleaved between transactions. So from that point of view, we can assume that a serial schedule is what we want because it always gives us the correct result. However, there are certain issues with the serial schedule. So in practice, it is not acceptable. What are the reasons? First of all, it limits the concurrency. In a serial schedule, because there is no interleaving, you have to wait for one transaction to be over till you can start the next transaction. So that's wasting a lot of valuable CPU time. So let's say one transaction is waiting for input output, the other CPU is lying idle because the other transaction cannot start before the currently executing transaction completes all its instructions. So it is a wastage of valuable CPU processing time. And if the sum of the transaction has got lots of operations, in that case, shorter transactions may have to wait for long transactions to complete all its operations. So the waiting time overall output, that is the overall time taken to complete the instructions, will be way higher in case of serial schedule. So is there a way out? Yeah, of course, there is a way out. And the way out is to determine which other schedules are equivalent to a serial schedules, and we allow these non-serial schedules. So what we have, the keyword here is equivalent to a serial schedule. So you have a non-serial schedule. If you can transform it into a serial schedule, if it is equivalent to a serial schedule, in that case, this you can allow this non-serial schedule also. So this will improve, or this will eliminate the issues that were there with your serial schedules only. So this process is known as serializability. Okay. So a serial schedule, as I said, will always give the correct result, while some serial schedules may give the correct answers, while some may not give the correct answers, as we have seen in many examples earlier. So we categorize these non-serial schedules that give the correct results as serializable. So you have non-serial and you have serial. This always gives the correct answer. Non-serial schedules, sometimes some of them may give correct answer, some of them may give Wrong answer. So we are going to categorize these non-serial schedules which give us the correct answer. We are going to call them serializable schedules. Okay. So what is a serializable schedule? The definition is given here. So a serializable schedule is a schedule S is serializable if it is equivalent to some serial schedule of the same n transactions. So if you have n transactions, so if your non-serial schedule is equivalent to some serial schedule, in that case, this schedule is called your serializable schedule. So these are your serializable schedule. So, and here a point to note is that but because it is equivalent or it is serializable does not mean it is serial. Okay, see, in serial, as I mentioned, all the instructions are executed for a particular transaction are executed at the same time, are executed completely. Only after that, other transactions can start. But in a serializable schedule, you have interleaving of operations. Okay, but the only other property that they have is that you can convert it into a equivalent serial schedule like this. Okay. So being serializable, what does it imply? Why do we need to check if it is serializable? So because we know that some non-serial schedules, if it is serializable, it will always give you a correct result. So it will leave the database in a consistent state. And also you have interleaving. You have the interleaving of the operations. And as a result, that inefficiencies of serial schedule will not be there because you are ultimately having your concurrent executions. Now, when we talk about equivalence of schedules, a very important term that we have seen here is equivalent. So the schedule must be equivalent to a serial schedule. So there are different types of equivalence. Okay, the first type, which is the simplest, is called result equivalence. Now, this may not be a very useful concept, but still, nevertheless, let us look at what it means. So result equivalent means two schedules are said to be result equivalent if they produce the same final state of the database. If they give the same state of the database, then they are called result equivalent. So here, if you see, if we assume that the value of x is 100, and we execute this, so edit x as 100 includes this. Okay, so here I have, here I have x is equal to x plus 10. Okay, so x becomes 110 and then write x. So it becomes 110. So here I have, this is another schedule. So read x, so it reads the value of x is 100. So it updates x is equal to x into this. So x becomes 110. We multiply by this. And then finally you write this, the value of x, 110. So they have these two schedules, they have the same result. Okay, so they are said to be result equivalence. But now this, you can see the operations are totally different. Operations are totally different, but it is just because of coincidence that they have got the same result. So result equivalence is a trivial equivalence. So it may be by coincidence also. Then next we look at schedules which are conflict equivalent. So what is conflict equivalence? Okay, so two schedules are said to be conflict equivalent if the order of any two conflicting operations is the same in both the schedules. So we had seen earlier what are conflicting instructions. So if I have of the same data item, I have a read and a write. Okay, so if it is a read, first one is doing a read, then a write, or one is doing a write and a read, or somebody else is doing a write followed by another write, then these are conflicting operations. Okay, so two schedules are said to be conflict equivalent if the order of any two conflicting operations is the same in both schedules. So if we look at this schedule, this is say S1 and this is S2. So in that case, let us look at the conflicting operations. So here T1 performs write followed by T2's read. So these two are conflicting operations. So we'll see that in schedule this also, first T1 performs a write and then T2 performs a read. So yes, these two conflicting, the order of the conflicting operations are same. Then here I have write X. So write X and write X. So here first T1 will do write X, then T2 will do write X. So here also first T1 does write X, then T2 does write X. Similarly, these two are non-conflicting because it is not on the same data item. It is on X and Y. So if you look at these two, these are conflicting. So first Y does a read, read Y, a write Y is from T1 followed by T2's read Y. And the same here for these two operations. So in these two operations or in these two schedules, the order of the conflicting operations are same. So these are known to be conflict equivalent. So the order of the conflicting operations of the two schedules, if they are same, then it is a conflict equivalent schedule. Then comes the concept of conflict serializability. So we saw conflict equivalence. Now you can see S1 and S2, none of these are serial schedules. Both of these are non-serial schedules. So here, if your schedule is equivalent, is conflict equivalent, to a serial schedule, then your schedule is said to be conflict serializable. So if I have S and S dash are my schedule. So if you see, are these two schedules conflict equivalent? So let's see. Yes, read write, T1 write and then read. So T1 write, then read. Then write, first T1, then T2. So first T1, then T2. For Y, these two are conflicting. So here T1 does write first, then T2 reads, yes. And the same here, write. So write. So these two are conflict equivalent. And because S dash is a serial schedule, so the schedule S is said to be conflict serializable. A conflict serializable schedule is one which is conflict equivalent to a serial schedule. So this is the concept of conflict serializability. Now, there is a way by which you can test if your schedule is conflict serializability or not. Okay, so for that, this is the algorithm. The way steps is done through, it is done with the help of creating a graph known as a precedence graph. So what we'll do is we will look at only the read and write operations, and then we'll construct a precedence graph. So what is a precedence graph? A precedence graph is a directed graph. So a graph consists of some nodes. So let's say T1 is one node, T2 is another node, T3 is another node. Okay, and then there are edges of the graph. Okay, so there are edges of the graph. So this is a directed graph. Directed because there is an arrow from T1 to T2. This is one edge. Then from T3 to T2. This is another edge. So this is another edge and this one is another edge. So a precedence graph will be something like this. Okay. So how do we create this precedence graph for your for testing conflict serializability? So first we'll do is for every transaction that is there in the schedule, we will create one node like this. For every transaction in the schedule, we'll create one node. Okay. And then the edges will be added to the graph based on this. So edge is created from Ti to Tj if one of the operation in Ti appears before a conflicting operation in Tj. Okay. So this is the algorithm. For every transaction Ti participating in schedule S, create a node labeled Ti in the precedence graph. Then draw an edge from node Ti to Tj if Ti executes write X before Tj executes read X. Okay, so write X is before read X of Tj, read X and write X and write X and write X. So if one comes before, if Ti executes a write or a read operation before Tj performs a read or a write operation, okay, on the same data item, then we will draw an edge. And if there are no cycles in the precedence graph, like you can see, this is a cycle. So from T1, I can go to this, and then I can go to this. And then again, I have another cycle here, this one. From here, I can go to this. From this node, I can go here. And from here, I can arrive at this. So this is a cycle. So if there are no cycles in the graph, then the schedules are conflict serializable. Let's see with an example. So you can see that we have one transaction here, schedule A, which is a serial schedule. Okay. Schedule B also, which is a serial schedule. These are both, you can look at the operations, they are both for the same two transactions, T1 and T2. A and B are serial schedule and C and D are non-serial schedules, as you can see out here. So let us draw the precedence graphs for C and D. Okay, we can start from T and for the first two also. Let's start with T1. So T1 has got two transactions. So I will draw two nodes for one for each transaction. Now, what was the condition for drawing the graph, for drawing the edge? If draw an edge from Ti to Tj, if Ti performs a write before read, read before write, or write before write. So for the same data item. So here you can see data item X is one which is common between T1 and T2. Y is only read by T1, so there is no issue here. So does T1 perform a write or a read before T2 does a write or a read? Yes, this one and this one. So T1 does a read and a write before T2's read and write. So we will draw an edge from T1 to T2 and label it on the data item which it is being read. So X. Similarly, for the schedule B, I have again two transactions, T1 and T2. Okay, if you look at this now, T2 is first. T2 performs a read and a write before T1 does a read and a write. So now the edge will be from T2 to T1. Whoever does before, the edge will be directed starting from that node and going to the other node. So T2 and to T1. Let's look at the non-serial schedules now. Okay, so here I have T1 and T2. All right. So here, if you look at these two operations, these are non-conflicting. So one must be a read, one must be a write. So these are non-conflicting. So no problem. Now here, T1, T2 does a read before T1 does a write. Okay. So I will have a graph from, I'll have an edge from T2 to T1. I'll label it as X. Okay. Then if you look at these two operations, these two are conflicting operations. So T1 does a write before T2 does a write. So T1 does a write before T2 does a write. So from T1 to T2, we will have another edge. So this is my precedence graph. Let us draw for the last one also, schedule D. So I have T1 and T2. Okay. So I have conflicting operations here. Okay. So I have write, T1 performs a write before read. Okay. So T1 to T2. Okay. Then again, similarly, this one and this one are already conflicting. So T1 does a write before T2 does a write. So again, it is on the same direction. So I will not have any more notes, because both of these, in both these cases, it is an edge that is from T1 to T2. So I have drawn it already once for this conflicting, or for this conflicting operations. So I will not draw again for these two. So this is your precedence graph. This is called the precedence graph. Now, what does our algorithm say? Our algorithm says that if there are no cycles in the precedence graph, then the schedules are conflict serializable. So let us see if there is a cycle. In the first two, these are serial schedules, so there cannot be any cycles. But if you look at this one here, you can see that there is a cycle. It starts from here, from T2 to T1, T1 to T2. Or you can start T1 to T2, T2 to T1. So there is a cycle. So this is not conflict serializable. However, in schedule D, you see, there are no cycles. So this is this schedule D is conflict serializable. And it is equivalent to which serial schedule? That you can know from the edge. Okay, so here I have T1 to T2. So it is equivalent to the serial schedule where T1 is done first and followed by T2. So here, this is the serial schedule where T1 is done before T2. Okay, so this schedule D is conflict equivalent to the serial schedule A. So this is the concept of serializability, conflict serializability. Okay, this is the algorithm. You have to draw the precedence graph. If there are any cycles, then it is not serializable. Otherwise, it is serializable. You can look at one more example here, T1, T2, T3. Now, 3 transactions are there. These are 2 schedules, E and F. And we can try drawing the graph for each of these. So you can see the output out here. So you can see for this graph, there is a cycle. You can see here, there is a cycle here. All right. And again, here also there is a cycle. This also is a cycle. So for this reason, this one is not serial. It is not equivalent to any serial schedule. However, look at the second one. If you look at this one, there is no cycle here. There's no cycle. Okay. From T3, you can go to T1. From T1, you can go to T2. But from T2, you cannot come back to T3. So no cycle. So that means this is conflict serializable. Similarly, for the third one also, you can see this is also conflict serializable. Now, your conflict serializable is a very strict rule on your schedule. So it is a little bit restrictive. So not all schedules will be allowed. So a little bit less restrictive definition of equivalence of schedule is given by another form known as view equivalence. Okay, so both view equivalence, basically it means that all transactions, both schedules must get the same view of the data. They should get the same data, value of the data. So it is less restrictive compared to your other schedules, equivalence schedules. So what is the idea behind it? That if a schedule is non-conflict serializable, then we check if it is view serializable. Okay. So already we have seen that some are this is not conflict serializable. So now next, what we can do is we can check if this schedule is view serializable. Okay. So all conflict serializable schedules are said to be view serializable, because we know that this one It is conflict serializable. This is conflict serializable. Now, if they are conflict serializable, they are already view serializable. Okay, but not vice versa. So if something is not conflict serializable, then we check if it is view serializable. So you can look at it as like this. If this one is, you have the superset is, your superset is all conflict serializable schedules are said to be view serializable, but not all view serializable schedules are conflict serializable. So if this is conflict serializable schedule, then, and this set is your view serializable. So the ones which are not conflict serializable also may be view serializable. So let's see what it is. So view serializability is if a schedule is view serializable if it is equivalent to a view equivalent to a serial schedule. So what is view equivalence? We'll just look at the definition and example. So two schedules are said to be view equivalent if the following three conditions hold. Three conditions only are there. First one, very simple. Both S1 and S2 should have the same operations. So here, if you see three transactions, T1, T2, and T3, okay, all of them, they have the same operations, right? T1 has read queue, write queue. T1 here also has got read queue, write queue. Here, T2 has write queue. Here also T2 has write queue. And here T3 has write queue. T3 here also has write queue. So they have the same operations. Then the second one is for any operation read X of T1, Ti in S1. So in this, any read operation, if the value of X read by the operation has been written by an operation write JX of transaction Tj, okay, the same condition must hold for the value of X read by operation Rix of Ti in S2. Let me explain this in this way. Here you can see there is a value which is a read. We are going to look at the read operations. So we will see that if is the value of Q, who has which other transaction has written the value of Q read by T1. Now in this example, it is not there. Nobody has written. It is reading it directly from the database. So suppose there was a write Q here. There was a write Q out here. Okay. In that case, we can say that the value of Q read by T1 was written by this operation in transaction T2. So in the other schedule also, there should have been a write Q of T1. So T1's, the value read by T1 should have been written by T2, transaction T2. Okay, but in our example here, there's only one read is there. So this value is read directly from the database. This is known as a blind read. So we don't need to have a we don't have that operation here. And the third condition is the same transaction should perform the last write on the data item X in both schedule. Now, who is writing the which in schedule S1? Which one is the which transaction is doing the final write? It is this transaction T3. So in schedule 2 also, T3 should be write the final value of Q. So I have here Q3, T3 is also doing the final write on Q. So in such, if all three conditions are satisfied, then we can say that the two schedules are view serializable. This schedule is view serializable. So as you can see in this example, this is a serial schedule. This is a non-serial schedule. Okay, it is not conflict equivalent because these two are conflicting instructions. Okay, and the order is different in both. So it is not conflict equivalent. Is it view equivalent? Yes, first condition, because same operations are there. Same operations are there. Same ops. Number 3, Qt3 does the final write. Final write. And the second condition, for any operation read X, So there's only one operation, read X here, read Q in our this. So read Q. Okay. Now the value of Q, which is what it reads, either it will read it directly from the database in both schedules. Yes, it is directly reading it from the database in both schedules. Or if there is another write operation, okay, then whatever was written by T1, T2 is read by T1. So here also write must have been before read Q of T1. So this is your view equivalence. So if what we have seen here as a summary, I can say that we saw that serial schedules always gives the correct output, but serial schedules are not very efficient. So because they are not very efficient, we have to allow non-serial schedules. But to ensure that we always get the right result, okay, we have to find a non-serial schedule, we have to find a serial schedule to which it is equivalent. So equivalence can be either result equivalence, which is again not much of much use, or it must be conflict equivalence, that is the order of the conflicting operations must be the same in both schedules. And the third is your view equivalence, view serializable or view equivalence. So it must be view equivalent to a serial schedule. So that is all about serializability.